Well, solving the differential equation with the Dirac delta function on the right hand side in Sage is pretty much the same thing we had to do with the Heaviside or unit step function. So I took that code that I'd used for the Heaviside function, and I just came in here and I said, oh, well, use the Dirac delta function instead. So then all this stuff was the same. I took the Laplace transform of the differential equation right here. I showed it. I defined the derivative and so forth again. So I could do that substitution for the initial values, showed that. Here I take the Laplace transform of x, and so that was my differential equation with the substitutions in. And let's see, so I think again, because I get to where I don't really have to think about it, I just throw things in. But so here I've got that Laplace transform, and where I'd solve the resulting differential equation that had been transformed for x, big X. And so then I tried doing the inverse Laplace transform, show that solution, and actually the same thing happened again. So if I evaluate this thing, we can see those pieces. So here was the transformed differential equation. This is kind of long, so it's hard to scoot over all the way, but there it is with our Laplace transform of the Dirac delta function at 3 right here. And then we have it with it being substituted. Here we solved for big X, or the Laplace transform of little x, and we have that solution, so that looks like what we did by hand. And then we try to take the Laplace inverse, and again this part up here was a problem because it wasn't expanded. It had that e to the minus 3s times everything, and so I did the expansion and we got all this stuff, the s and the +4 here, no problem. So then I take the inverse Laplace transform of this expanded one, and of course we get our usual suspects here that were just fine. That first part for the s +4 over our s squared plus 4s minus 21 worked again, but it still didn't know how to do that time shifted thing. And so just like before, I simply took the bottom, well, the bottom, in this case the bottom, because it's just 1 times e to the minus 3s. But so I took everything except the e to the minus 3s, and I did the Laplace transform of that, and we see that we get exactly what we did when we did it ourselves. We get the minus 1/10 times the 1 over s plus 7, and we get the plus 1/10 times the 1 over s minus 3. So then I do the inverse Laplace transform of that, and this is the unshifted answer to this thing up here. But you have to remember it had this shift in it. We can see that with the e to the minus 3s. So it had that shift, and so the actual answer for this part is that we had to multiply by our Heaviside function or unit step function, whatever we want to call it, at t minus 3 or of t minus 3, And then here you see that we had the 3 times the quantity, t minus 3, so we got 3t minus 9. And here we had minus 7 times the quantity of t minus 3, so we got minus 7t plus 21 with the 1/10 outside. So that is this portion of the answer. So to get my full answer, I need to remember to get these first 2 terms and then add to that this final term with the Heaviside or unit step function involved, or that piecewise function. And pretty quick, really. Now that, since I knew how to do the Heaviside, pretty much you go through the same things. This looks almost exactly like when we started with the Heaviside function. The difference was that this term in the middle, in this case, with the Heaviside function, because its Laplace transform was e to the minus 3s over s, the degree of this denominator here for this part was 1 bigger. It was s, we had s cubed plus 4s squared minus 21s because of the Heaviside Laplace transform. But other than that, they look pretty similar. They both cause, whether we have a Heaviside over there or a Dirac delta, they both cause this shift or a piecewise defined solution. So again, the solution always has this portion in it, but this portion here, well, I missed the 1/10 there, but that portion doesn't come into play until we hit t equal 3. And that's what the Heaviside does for us. And again, that makes sense from the original differential equation. It says, hey, we've got this homogeneous equation until t equals 3, then all of a sudden there's a big impulse. So we would expect something different to happen after that. So if you think about it that way, it all makes sense. We simply are solving, in essence, the nice part with the Laplace transform is we're solving a piecewise defined differential equation, but we're more or less solving it all at once. And if Sage Math knew how to do this inverse Laplace transform, it truly would seem like everything at once, and we would just get that answer. So that's one thing the Laplace transform here does for us. All right, well, we'll call that good. So that's using Sage Math to do that Dirac delta problem.